So, hello everyone, welcome to week 6 of NPTEL course Coherence and Quantum Entanglement. We have reached to 50% of the course as it is week 6. So, already we have covered up to 50% of the mentioned syllabus. So, till now, all of you are very well aware about this course and the details of it. So, I will just mention those once more, as I always do at the starting of every discussion session. So, this is NPTEL course Coherence and Quantum Entanglement, which is instructed by Professor Anand Kumar Jha, and I am your TA Nilakshi Shanapati, and we have a problem solving and doubt clearing session on every Saturday 5 p.m. to 7 p.m. So today is the week 6 and we are at 6 discussion session. We have already conducted 5 discussion sessions and lot of discussions, lot of problem solving problems we have solved. So now the 50% of this course was mostly dedicated towards coherence, whereas we are for the um, next 50% of the course we'll talk about quantum entanglement and the related things, and mainly the today is the starting point of that. So first, today we will do lots of problems, like we will do 5 or 6 problems related to several things, and mostly coherence, mainly orbital angular momentum, azimuthal degree of freedom, because those problems I left because in the quizzes the WAME degree of freedom was running, and as your quiz submission date is over now, so today we will discuss about orbital angular momentum basis problem solving, and we will discuss several problems, and then we will discuss today about the spontaneous parametric turn conversion, which is a nonlinear optic effect which we observed in second order nonlinear crystal. That is very important, very interesting, and this is the starting point of your main interesting thing, that is the quantum entanglement. So the next 50% will be much more important and much more interesting for you. So okay, so before starting the class, as I always mention, today I will again mention about the now the Google Drive folder link and the YouTube channel link where you can find this recorded session. The YouTube channel link is this. Where this is a YouTube channel link where you can find the video of a recorded session of this discussion, recorded videos of this discussion session, and this is a Google Drive link which I am sharing, where you will get all of the needed documents and whatever I used to discuss those PDF files, these slides, PowerPoint presentation, some syllabus, some extra materials which I used to provide to you. All of them you will find in this Google Drive folder link. And again, I will mention my email ID. I'm mostly available in via mail, and whoever used to mail me, I usually give reply to them and try to motivate and guide properly, such that you can learn most part of this course, and mm, this is what we aim for also. Okay, so all right, okay, so today we will start with our quiz and homework problem. This problem I showed to you on the previous class, where we were like I showed this problem to you. I gave this as homework. The last D part was homework problem. This part C was quiz problem which you got in your assignment. I hope everybody of you have submitted and perfectly done this problem, because I have already given you the hint in this problem where A and B are written. So today we'll start from doing the C and D part, because C was in the quiz and D was what I gave you as a homework. And if anybody of you have any queries, then you can write into the chat box of this Google Meet. And if you miss this class and have question later on, then you can uh, mail me, or you can write into the chat section of or comment section in the YouTube. So I will start this, but before that let me wait for a few minutes, such that wait few minutes for other students to join. I will wait 2-3 minutes. Okay, so let's wait, and then I will discuss about these two problems. And one more thing, today my health is not very well. I have fever and cough and infection in throat infection. So in between, maybe I can take 1 or 2 minute rest, because my otherwise my throat cannot permit. So please bear with me for that. Sorry. So let us wait for 2-3 minutes for this for other students to join. So let us start with this. So consider a one-dimensional. It is saying. Let me start. Let me reread this. Read this problem again for you. Where it is telling that consider a one-dimensional, spatially completely coherent field Vx equal to 0, x z equal to 0 equal to a, that is a constant thing, passing through a phase screen of negligible thickness kept at z equal to 0. The screen imparts a phase phi x z equal to 0 to the field. Calculate the cross spectral density and the degree of coherence function right after the phase screen. When phi equal to phi 0, where phi 0 is constant, that for that condition we have calculated mu was 1. For when mu equal to x equal to z equal to 0, if the function of x, if it's any function of x, that also we calculated mu was 1, but w, that is the cross correlation function, was different. Now part C is saying when the phase screen is such that it changes randomly in a continuous manner with phase equal to kx, here k is k is a random variable with probability density pk equal to 1 by root over 2 pi sigma square e to the power minus k square by 2 sigma square, then what will be the degree of coherence at cross spectral density function? So let us calculate this. So here Vx z equal to 0 is equal to a to the power I k x. I hope everybody of you can see this. Now Wx1 x2 z equal to 0 will be V star x1 z equal to 0 V x2 z equal to 0, which is equal to a square e to the power minus I k x1 minus x2. I am just substituting all of this, okay? Whatever this is x at x1 and this is as x2, the difference between them, and then whatever I am getting, I am writing that, because it is mentioned that pk, the probability density function, is 1 by root over 2 pi sigma square e to the power minus k square by 2 sigma square, which, and this is the probability density itself. So now this is the probability density itself, and this I can write like this, as we all know how to write the expectation value, and we have learned how to write this in the correlation in terms of integration whenever we have in terms of ensemble average, and how will I write in that integration form. We are already aware about that, and this pk, probability density, is provided. Now I will substitute that. Now after substitution, if you calculate the integration is a standard integration, which I have already mentioned that this kind of integration you will find again and again in this course, and you need to know how to solve this, and I have already given you that what are the tricks and how to solve this kind of integration problems. These are some special integrals which need common function integration as well as some special common function integration. So you can directly then calculate and solve and write the directly write can you can directly write the solution of the integration. So I will not tell again, that I have already mentioned several times. Now I will directly write it. I have already solved the question previously by myself, so I am not solving step by step again. I will directly put it here, and so finally what we got is a final result. So this is the cross spectral density or cross correlation function, or I mean cross spectral density, which is mentioned here. Yes. Now we'll find the mu, that is the degree of coherence. This is the intensity at that particular point, which we can write as W as x1 x1 and W x2 x2. The same thing we did for the same thing we did for previous two problems, A and B part also. Okay. So this will be the answer for degree of coherence. And it is, this was the part C, and for the last part D, it is saying, for the last part, calculate the spatial coherence length of the field right after the phase screen. The spatial coherence of the field after the phase screen will be this 1 by sigma. We know how to calculate. I have shown to you in the week 4 class, I think week 4, that how what is degree of coherence, what is spatial coherence length and all those things. So here it will be by sigma. So this is the problem of this was in quiz plus homework. I hope you can understand that these kind of problems are very important, as it is coming in the quiz and homework. You can expect this in end semester also. Now we will solve this next problem, which is showing over this, showing here in this slide. I'll again wait for 2 minutes such that other people join. There are not many people in today's class, so let us wait for 2 more minutes where I will start solving this problem. So it is saying consider an optical field V phi that is coherent superposition of modes carrying wave index L and minus L as V phi equal to e to the power I L phi plus e to the power minus I L phi. What is the azimuthal correlation function W phi 1 phi 2 in the part A, and part B it is saying what is the corresponding azimuthal intensity S phi. So we'll calculate those now. Okay. The first question is what is the azimuthal correlation function for this? So the azimuthal correlation function is I am calculating all of them step by step. Just follow. I hope there will be no problem in this time because I have already, I mean, you guys are already aware that how to solve these kind of problems. We have first solved for temporal degree of freedom, then we solved for a special degree of freedom. Now we are solving it for azimuthal degree of freedom. If you calculate this, then it will be 2 cos L phi 1 2 cos L phi 2, which will be equal to 4 cos L phi 1 cos L phi 2. So this is the first question. We found the answer. This is the azimuthal correlation function. Now in the part B, they are asking what is the corresponding azimuthal intensity. Very easy. Azimuthal intensity is equal to I phi W phi phi equal to what? W phi phi means 4 cos L phi cos L phi, that means 4 cos square L phi. This is the azimuthal intensity. This is the answer for the first part. This is the answer for the second part. Okay. This is a problem 1. Now we will do this problem number 2, which we are showing, which you can see here in this slide. But before that, I will again wait for a few more minutes for some students to join, and let us wait for 2 more minutes, then I will start discussing about this problem. Now it's problem 2, which is saying the angular correlation function for the Gaussian cell model pump field is given by AQ1 Q2 equal to this. What? Let me write what it is given. Where A is constant, so that the cross spectral density function W rho 1 rho 2 at Z0 is this equation 2. This is equation 1. So you need to show this. Where alpha equal to sigma square, sigma mu square plus 2 sigma square, beta and so on. Beta is like this, delta rho is this. 1 minute. Here sigma s is the size of the beam at z equal to 0. Sigma mu is the transverse coherence width at z equal to 0, which is the distance scale over which the field at z equal to 0 remains spatially coherent. So this we need to show basically W. For that, I will start directly by writing the cross spectral density at z equal to 0, which is 1 minute. Is how I am writing this equation for that question. This is already taught to you, and even if it is not, then the detailed calculation for the above equation is given in Mandel and Wolf section 5.6.4. Now AQ1 Q, this is let this equation is 2. Now this one is already given, which is this AQ1 Q2, which is the angular coherence function. Now we will substitute that AQ1 Q2 in this equation 2, and we'll use the standard Gaussian integral what we are using till now. So let me first substitute. Now alpha beta is given to you. We need to write in terms of them. Alpha is sigma square, sigma mu square plus sigma 2 sigma square by sigma mu square plus 4 sigma s square and beta is 2 sigma s to the power 4 sigma mu square plus 4 sigma s square, this alpha and beta, and delta rho is equal to rho 2 minus rho 1. Now I will write the direct solution of this W rho 1 rho 2, that is the cross spectral density at z equal to 0 in terms of this parameter alpha beta delta rho. Now you can, of course, you can calculate this according solve this, find this each and every step, and I mean you can calculate each and step by step and check if you are getting this or not. Some a dash, there will be several things in front which you can consider there, which is, I mean, those we are not interested about, that's why I am not writing, just writing at a dash. Then rho 1 square by 2 sigma s square e to the power minus rho 2 square by 2 sigma s square minus delta rho square by 2 sigma mu square. Okay, so we will get this. Again, you can write this as a dash root over of s rho 1 s rho 2 mu delta rho. So we have proved this equation. I mean this one. Okay, so this was your first question, problem A, part A of problem 2. Next it is telling that calculate the far field expression at very large z for the cross spectral density function W rho 1 rho 2 z. Take the central wave vector to be k0. I hope you can understand what we need to do. We need to do the we need to just do the far field thing just by using the Van-Sitter-Jarnicke. So I'll just calculate directly, because these things we have used several times and done by now several times for temporal degree of freedom, spatial degree of freedom. Now it is azimuthal degree of freedom, but the solution are very tedious. You need to do it very carefully, and you need to have some patience to solve these questions. One minute. All right. I don't need this. Now substituting the expression of angular coherence function, that is AQ1 Q2 here. What is AQ1 Q2? Let me write that there also. Again we are using the standard Gaussian integral which we are doing for several times now. Then what we'll get, I'll directly write, you just check by yourself. You need to substitute these and do step by step solution. By yourself and check the result. I am giving you the result, which is okay. So please ignore my background noise. Sometimes it is noisy very much, so please don't please be considerate with that. Now what is sigma sj? That is equal to, and what is sigma mu z? Okay. This is called RMS beam radius of the field at z in the far field. And this is equal to RMS spatial coherence with at z, which is far field. Okay, so this is the problem. This is a solution. This is a result that you will get. This is a part B. Now we'll talk about part C. Part C, it is telling, in the last part we find that the transverse coherence length of the field depends on z. In this part, find an angular correlation function of finite transverse spectral width delta q such that the transverse coherence length of the resultant field is finite but does not depend on the propagation distance. Alright, very simple. The cross spectral density function at any z is given to us with this equation. Now we will substitute aq1 q2 as sq1 delta q1 q2, because it is mentioned that aq1 q2 of the finite transverse spectral width such that transverse coherence length of the result is finite but does not depend on the propagation of the distance. That's why. Now if we substitute that, then we will we need to show that we find the cross spectral density does not we need to show this in the last part we find that this is given in this part. Find an angular correlation function aq1 q2. We need to find this aq1 q2, that for what this the transverse coherence length of the result is finite but does not depend on the propagation distance z, that we need to find. That means what will be the aq1 q2 that we need to find. And this is very intuitive in nature. We can intuitively think that what we can what will be, it will be just delta function, because if it is delta function then we can see that it will propagate, the cross spectral density will propagate but does not depend on the jet. Therefore but now let me write it properly, then you will it will be documented very well and you will be understanding it in the later half also if you are not here present currently. The cross spectral density function at any jet is w rho 1 rho 2 jet equal to 1 by k to the power 4 integration minus infinity to infinity a q1 q2 a q1 q2 with or minus I q1 rho 1 I q2 rho 2 with or minus I q1 square minus q2 square by 2k z d2 q1 d2 q2. Now if a q1 q2 equal to s q1 delta q1 minus q2, then if we substitute this to this, we'll find this like this, which means now the cross spectral density function does not depend on j. Therefore we conclude that the transverse coherence with also does not depend on j. Okay, so this is the problem 2. Now we'll discuss about problem 3 and problem 4, but before that I will again take some break before problem 3. Let us have 2 minutes or 3 minutes break again, and then we'll come back and solve this problem 3. Okay, let us start with our next problem, which is problem 3. But it is saying the field amplitude u rho z is written in the paraxial approximation as u rho z equal to the power ikz integration aq and this whatever given, where aq is the angular spectrum, k is the wave vector of the field, and q is equal to modulus of q. Then it is asking derive an expression for the cross spectral density function w rho 1 rho 2 z. I hope you have understood what you need to do in terms of the angular correlation function a q1 q2. Then we will understand what is b and c. Let us first solve this part A. Very easy. Excuse me. 1 minute. Let me write this u rho z first. Therefore, we can write the cross spectral density function which is nothing but as the cross spectral density function is this, and the quantity aq1 q2 is nothing but it will be a star q1 a q2, which is equal to I q1 square minus q2 square by 2k into z, which is into d2q1 d2q2. Now if you write, you can write this as integration minus infinity to infinity a q1 q2 to the power minus I q1 dot rho 1 plus I q2 dot rho 2 where I q1 square minus q2 square by 2k into z dq1 d2q2. So this is the cross spectral density function. Very easy. Now the part B is saying if a q1 q2 equal to I q1 delta q1 minus q2, write down the expression for w rho 1 rho 2 z in terms of iq. It's also easy, we need to substitute this and we'll check what we are getting. So what is mentioned? Mentioned that a q1 q2 equal to delta q1 minus q2. So w becomes w rho 1 rho 2 z equal to minus infinity to infinity I q1 rho the 1 minus I q1 dot rho 1 minus rho 2 dq1 equal to minus infinity to infinity I q 1 minus iq dot rho 1 minus rho 2, right? Because q1, if I can write this as q1 means q2 or q whatever you can write, because there is no q2 here, and q1 needs to be equal to q2, then only we can write it in terms of one of the other one of the, I mean in terms of q1 or q2. This means this Dirac delta function means what? That means it is same at the same point, otherwise it is not same. Because the Dirac delta function involved, so the integral contributes only when q1 equal to q2, and therefore the cross-spectral density function ends up being independent of the propagation distance z that we can see here. Now the part C. Part C, it is saying consider two correlated point sources kept at the back focal plane of a large thin lens kept at z equal to 0, such that each point source gets converted into a plane wave, resulting in the angular function right after the lens at z equal to 0 being this one. Find the expression for the cross spectral density and corresponding intensity. Alright, we'll do so. Whatever it is saying. So now A is given like this. So W rho 1 rho 2 Z will be equal to I hope you are understanding that step by step things. You can solve it step by step according to your convenience and understand the steps. Whatever I am doing is very straightforward, and I have already done this by myself previously, so I am writing it very fast. Otherwise, I will not be able to complete all of the problems. So please try it by yourself at your home, and solve the steps, do the steps by yourself also. So this is the cross spectral density, and the corresponding intensity is I rho z equal to W at rho z, which is equal to 2 only. Why? Because this cos q0 my dot rho minus rho means 0, that will be equal to 2. So this is the answer. So here it is told to you that find the cross spectral density function. This is the answer. And second is this corresponding intensity. This is the answer. So this is the problem C. So we have solved 3, 4, 5, 6, 7, 8, 9, 10. 10 problems already. Now I will again take 2 minutes break and solve the problem 4. You can read this problem 4 meanwhile, and then I will start solving the problem 4. Okay. Okay, so let's start reading this problem. It is saying, consider the situation shown in the figure below. Figure here. A stochastic field V5 falls onto an aperture in the form of double angular slit with V5 equal to as given. Let me write that. Where alpha L star L1 star alpha L2 star is given to you. Let me drink some water. I am feeling very coughing. Consider the angular slits to be infinitesimally narrow. That is, take the aperture function to be phi of phi, big phi of function of phi, equal to delta phi minus phi 1 plus delta phi minus phi 2. The detector dA measure the intensity in a mode with orbital angular momentum index L. Derive an expression. Let me write the other things also. Then I will read A and B and we will solve them. Okay. Now problem A is saying derive an expression for the intensity at the detector as a function of OM index L. I have already showed this in a figure to you and told you to try that this will give you the intensity pattern, petal pattern. So I mean intensity. So let us now calculate that what it actually will be. So part A. First we need to calculate alpha L. I showed you the formulas previously also in the previous class. Now I will directly use them. This is just nothing but the Fourier transformation. I am applying the Dirac delta function properties and using it for the integration and writing the next line. Okay. Now you can write this V5 again like this in summation form, which will be, now it is L dash. These are dummy variables. Previously we used IL, that's why we are using here now IL dash, because this is something else, not the same thing, to represent that only. Okay, so this is now the alpha L in terms of alpha L dash, and L dash L phi 1 phi 2. Now we are using this alpha L star alpha L dash equal to C L delta L dash. Why this? Because this thing was given to you as in terms of L1 L2, as we are using L and L dash, so we are writing like in L and L dash form. Simple similar thing. In spite of L and L dash, you can also write in terms of L1 L2. Whereas alpha L square equal to alpha L star alpha L. This can be written like this. You do all of the in between calculations, then you will find this. So derive an expression for the intensity at the detector as a function of the OM index L. Okay. So this is the answer. Now the next question, problem part B. 1 minute. It is saying find out the explicit expression for the intensity at the detector as a function of the OM index L when CL1 equal to 1, for L equal to L0 and CL equal to 0 otherwise. So alpha L square becomes 1 by 2 pi square one plus cos L0 minus L del phi. So this is the answer. So we have found out the expression of intensity at a detector where this condition is given to you. Okay. Alright. So these were the problems that I wanted to discuss. Now after this, I want to discuss with you few important things, and we'll now formally start about the quantum entanglement. So for that, we'll introduce quantum entanglement and basics of nonlinear optics today. Before that, let us wait for 2 more minutes before this discussion starts, and then I will again start to discuss about the nonlinear optics, and what is spontaneous parametric down conversion, what is you also learned about the difference frequency generator, some frequency generation in your lecture, and today we will discuss about spontaneous parametric down conversion with slide, and I will formally introduce the quantum entanglement. So let us have a break of 2 minutes again, and then we will again start. So, as I mentioned, let us formally introduce quantum entanglement. So, in 1935, Einstein, Podolsky, and Rosen recognized a spooky feature in the quantum description of physical reality. This feature, now known as entanglement, which implies the existence of global states of a composite system cannot be described as a product of the states of the individual subsystems. Now, for an extensive review of the subject quantum entanglement, we need several papers to study, and you can have some review paper on this to have a overall idea. There are several like this. If any one of you want to go deep into this and want to study the papers itself, then let me know. I'll share the papers with you, or paper names with you. Papers details with you. Then you can check it by yourself. Now, Einstein, Podolsky, and Rosen were explicitly considering a system of two entangled particles which had once interacted in the past but had no interactions thereafter. And they showed that in such a system, by measuring either the position or the momentum of that particle, either the position or momentum of other particle can be predicted with complete certainty without in any way disturbing the other particle. But this position and momentum, we know they are non-commutating observables. They cannot be measured simultaneously and thus cannot be regarded as simultaneous elements of reality of a system. So they concluded that in entangled two particle system, the reality of position and momentum of the second system depend upon the process of measurement carried out on the first system, which does not disturb the second system anyway. And by noting this apparent non-locality in the quantum theory, Einstein, Podolsky, and Rosen argued that the quantum mechanical description of physical reality is not complete, and it should be supplemented by postulating the existence of hidden variables. The specifications of these will predetermine the result of measuring any observable of the system. This Einstein-Podolsky-Rosen's inherent belief was that the prediction of quantum mechanics are correct, but only as a consequence of statistical distribution of hidden variables. This was going on until mid 1990s. Now the studies related to entanglement were mostly centered probing the foundations of quantum mechanics. And we found currently it is very much well, there are several works, several things have been done. Quantum entanglement is now a very well established theory as well as experimentally demonstrable thing. So now it is very much prominent and it is well proven that quantum entanglement actually occurs, and this is the reality. And you know that Alan Aspect, Geilinger, and Alan Aspect, Anthony Geilinger, and I am forgetting the other person name. The three of them won Nobel Prize in 2022 for their remarkable work in quantum entanglement. And in recent years, entanglement is beginning to be seen as a resource that could also be used for many useful applications. And some of them are like quantum cryptography, quantum dense coding, quantum teleportation, entanglement swapping, quantum lithography, etc. etc. We are now going in detail on the process of two photon entangled states. We will do so, we will discuss that. And this process is called spontaneous parametric down conversion, which is a nonlinear optical process. So the basic of nonlinear optics is already described there in your lectures. So I will not go through all of this equation and the basics of nonlinear optics. You have even seen the second order nonlinear optical effects like second harmonic generation, sum and difference frequency generation, and parametric down conversion is also told. But we'll discuss some few things. Among them, spontaneous parametric down conversion is there you learned about some frequency generation, difference frequency generation. Those are off conversion, and now we want to but our main focus will be the spontaneous parametric down conversion, that is a down conversion, because through this process we actually can generate this entangled 2 photon. Okay, so I will now explain this thing with this figure. But before that, let me drink some water. I'm feeling itchy. I'm feeling uncomfortable. So I will resume in 2 minutes. Okay, so now let us discuss this. So here in this figure, you whatever you are seeing, that is a spontaneous parametric, showing that entangled photon generation through spontaneous parametric down conversion. Spontaneous parametric down conversion is a process, is a second order nonlinear optic process through which we can actually generate two entangled photons. Here it is showing that a pump is coming and falling on a crystal, which is showing with this, which is chi2, that means second order nonlinear crystal, and passing through a band pass filter, and we are collecting, why, because this is those are technical details, but suppose the omega p, the pump is of omega p frequency, which is corresponding to suppose 405 nanometer, then after passing through it, it will produce two photons of different frequency. Those are two photons of different frequency than the pump photon, and which are called Signan and Idler, of 810 nanometer wavelength, which are spatially separated but intrinsically correlated. That's why they are entangled, which are non-local itself. And the process of generation of this entangled photon is called the generation of entangled photon through the spontaneous parametric down conversion. From now on, it will be it will be our bread and butter. And the total moment if you ask me the question that why this happens, this just happens because of two utmost truth of nature. Those are energy conservation and momentum conservation. You can see energy conservation is showing with this, where omega p is going up and omega s and omega I are coming down. These are that is equal to, that is omega p equal to omega s plus omega I. And for the moment, this transfer momentum conserved, which is q equal to qs plus qi, we have already mentioned several times that we are representing the momentum with q, transverse momentum with the q, and transverse momentum is conserved always. Now I have shown this Ls and minus Li, which are orbital angular momentum of Signer and Idler. Though if you do sum of them, then total orbital angular momentum will be 0. That means that is also conserved. So due to the utmost truths of nature, which are the energy conservation and momentum conservation, this happens. And this process is called spontaneous parametric down conversion. And this is not only the one process through which we can generate the entangled photon, but this is the most celebrated and most useful and mostly most realizable and most realizable process, which through which we actually generate. And if you ask me, then yes, we used to generate in our lab this entangled photons using this SPDC process. And for that we use this SPDC chi2 crystal, that is second order nonlinear crystal, which is called and the crystal is beta borium borate, which is called BBO crystal. And there are several stuffs regarding related to this spontaneous parametric down conversion. If you want to read, then I can give you some very useful very useful what I can say, references. So and you can visit our website, our group website, where you will get many many papers related to this. And this is one of the very nice paper. Uh, let me tell you, this phase matching in beta barium borate crystal for spontaneous parametric down conversion. This paper is actually very helpful and very for understanding the spontaneous parametric down conversion, if you want to do so. I am giving the detail of this paper in this chat box. Please find it yourself if you want to study more about this. And already there are several papers given in this slide. You can find them if you want to study more. And for the nonlinear optics, the best book is by Robert Boyd, and you can find each and everything of this second order of this nonlinear effects and nonlinear optics. This very detailed book, very nice book. You can study this. Now I have represented not me, but this is that this process can be represented with this ITP, the function, the state function which is generating through this process, like somewhat like this equation in several degrees of freedom. Like this first equation is written in the position momentum degree of freedom, the next it is written in the orbital angular momentum degree, angle and OM degree of freedom. So where SL is called as the OM spectrum. So these are very detailed, and these are currently research area. We research in this, we work in this. So if you are interested, you can always find these things, and that how we got this psi TP, that is the two photon wave function, that you have already learned in your lectures. And if you need any help to understand these things, then please do write in the chat section, or ask a question portal, or in YouTube, or whatever, if or do mail me. And why we are calling this as entangled state? Because these two states are non-separable state. That means signal and idler, we cannot write it in terms of Smith decomposition. That means we cannot do Smith decompose of this of this function. That means we cannot do psi TP equal to psi s cross tensor product cross psi I. We cannot do this. If tensor product and Smith decomposition can be done, then it will be a non-entangled state, but this is entangled state, that's why we cannot do this. So this is through this we can say that this is this state, whatever we are saying, that is a non-entangled, that is an entangled state. Okay. If you ever get some problem like this, that some state is given and you need to state that if it is a entangled state or non-entangled state, that means separable state and not, I should not mention about entangled, not non-entangled now. Rather than if you are asked that if it is separable state and if it is non-separable state, just ask in question like quiz or assignment, then you can just do the Smith decomposition. You can check that if you can do Smith decomposition, or if you can do the tensor product, you can write the state in the tensor product or not. If you can write, then it is a then it is a separable state, and if you cannot write, then it is a non-separable state. And this entanglement can be observed in various degree of freedom, like time energy, position momentum, polarization, angular position, OM. So these are the several few paper lists that I have provided, that if you want to study and go deeper into this, then you can find this. And I just want to mention that entanglement is observed, can be observed in various degree of freedom, and this is very much basis and basis dependent thing. So if you want in time energy, then time energy, position momentum, and in every degree of freedom you can observe this entanglement. Okay. And for each of them you can find these papers if you are interested to study more on this. So this is what I wanted to mention in today's discussion session, all of the things I have mentioned now. So I will not take much time I will not take more time and if you have any question, then I will wait for 2 minutes. You can ask question, and then we will wrap up the session. Do you have any question? Please let me know. All right, if you do not have any question, then let's wrap up this session. As usual, I will say again, this was the week 6. Let me again. This was the week 6 class where we discussed, we have solved about 13 problems, and we discussed about spontaneous parametric down conversion. We formally introduced quantum entanglement, and I have given you several references, books, such that you can find them if you want to study and go deeper into this direction. And so this is all from my side and for today. And for the recorded session, you can go to my YouTube channel, where you will get the recorded session of this classes. And you can go to the You can go to the drive folder link. I have a link is already shared by me as well as by the SWAM portal. That you can go to the drive folder link and check whatever I am uploading. So these are the necessary things that you need to know and you need to follow. So I hope everything is fine with you, and see you in next class. Till then, you practice this. You have any question, do write me, and use every possible way that you can use, that you have to learn this course. All right, so let's say goodbye and wrap up today's class. Bye.